All right, so we are moving on. We talked about just a second ago that, oops, that the probability in flipping the coin, that's still 0.5, and the rolling a 6 is 1/6. And shooting until we make the last shot, our probability is going to be the shooting percentage. And in comparison, we talked about how with the binomial, the number of trials is fixed and the number of successes is unknown. But with a geometric, the number of successes are fixed. It's going to be 1, whereas the n is unknown. And so we're going to look at the example of rolling a die until you get a 6 and looking at that. Okay, so how do we do that? Well, I'm not going to do the whole thing, but it's a little bit broken down on page 465. You can see. Okay, rolling a 6 is what we're interested in. And so we're kind of thinking about this like what we did before, where we would do each one is going to be given in a distribution function, where I'm going to have x and the probability of that x happening. Right? What's the probability of that happening? So what's the probability that it's going to happen the first roll? Right? What's the probability? It's 1 out of 6. That's right. Okay. Now, the second roll, what's going to happen? Now, in order for it to take, are we okay on the first roll, right? 1 out of 6. So for it to happen in 2 rolls, what has to happen on the first roll? It's not a 6. That's correct. So we're going to have 5/6 of the time, right, times the probability that happens on the second roll is still 1/6. And because these are independent, I can multiply those together. Right? And we should see a pattern is going to really emerge here. Well, maybe let's go out to 4, and then we'll do dot, 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 right? So if it's going to happen on the third roll, we're going to get a 6 on the third roll. That means what happened the first 2 rolls? Something else. And what's the probability that's going to be something else? Well, 5 out of 6 times it's going to be something else, times 5 out of 6 times it's going to be something else, and then 1 out of 6. Right? That last time, there's only 1 out of 6 chance, but we're going to stop there. And then if I want to fit this in, I could just say it's 5/6 to what power? And for the fourth one, to the third, yeah, because the first 3 are going to be something else, and then the last one's going to be 1/6. So what we can see is some very important things pop out. P in this case is 1/6. That's the probability that we're going to have success, and we can see that the first one is 1/6, the second one has a 1/6, the third one has a 1/6, the fourth one has a 1/6, right? And then this 5/6, where do I get that? That's 1 minus p. It's 5/6, right? So if this were some other probability, this 5/6 would just be 1 minus the p-value. And we notice that it also occurs here, right? Then 2 times, then 3 times, and so on, right? And up here, our value x could be, right, 1, 2, 3, 4, and it could just continue on, right? So what that means, let's extend this just a little bit. Let's kind of formalize this. We want the probability that x, this is the number of trials, equals a specific number, a specific, like, for n. We'll let these be the n values up here. Right? What's the probability that x is going to equal n? All right. And so this is kind of condensed, I think, down here, like on the top of 466, is that we're always going to have what probability in there? 1/6. So that's going to be p, and that's the probability for that last trial. And then to get these, right? You're going to have the other probability, which was 1 minus p. And it had a certain exponent, right? Here it was to the third, here it was squared, here it was to the first, and here it was to the 0th, because we didn't have any, right? We got it right the first time. So let's look at it. N is 1, and we had 0 of them. N is 2, and we had 1 of them. N is 3, and we had 2 of them. So this should be N minus 1. Okay. So then at this point, let's calculate what's the probability that it's going to take me 7 rolls to get a 6.